Hey everyone, welcome to 8.1. So we're going to be constructing confidence intervals to estimate or kind of get a sense of what the true population mean is. So to construct a confidence interval for a single unknown population mean, right? So you can think about this as we're guessing the true mean, right? It's a parameter because it goes with the population. And where the population standard deviation is not known. So this is essential that you have to be aware of whether you know the population standard deviation. And the way we're going to do that is we're going to create a point estimate. We're going to kind of take a guess at what mu is. That's kind of a weak analogy, but that's okay. I'm going to roll with it. And what we're going to do is we're going to create a margin of error. And then what we'll do once we do that, so we kind of like start with a point. We're like, hey, this is X bar, it's our point estimate for mu. It's a guess of what mu is. Again, this is a statistic. X bar is a statistic because it's going to come from a sample of the parameter, and we're going to use it to predict, estimate, guess, whatever you want to call it, the parameter mu. And then what we do is something kind of sneaky is we build this confidence interval. It's also very confident. Maybe we want to have a 95% confidence interval, or we want to have a 90% confidence interval. So we pick a confidence level, right? So that could be something like maybe it's 95% or maybe it's 90% or whatever, right? That's your confidence level. And then the confidence level is considered to be the probability that the calculated confidence interval, which is this shaded region right here, or rather the set of all values, the set of all possible outcomes here. This is your confidence interval. The confidence level is considered the probability that the calculated confidence interval estimate will contain the true population parameter. That's how most people think of it. But if you were being more mathematically rigorous, you would really say that the confidence level is the percent of confidence intervals that contain the true population parameter when repeated samples are taken. And so most of the time they're going to give us the confidence level that we want, but like, let's say you're a researcher, or maybe you're doing a kind of graduate level statistics project, or maybe you're even doing a science project, for, I don't know, pick something. Typically you are going to decide what your confidence level is. For the sake of elementary statistics, we're going to tell you what your confidence level is. Okay, so just to kind of get used to the idea of what we're doing, we are going to start with a point estimate, which is X bar. And then we're going to determine this error bound for a population mean, or the EBM. And you can also think of this as maybe the margin of error. Sometimes it's called that. Right, so we have our idea of our point estimate, X bar, and then we have our margin of error, or error bound for the population mean. And basically what you're doing, you can see here in this diagram, or even here in the structure of the confidence interval itself, is you're just starting at your point estimate, and you're going to go to the left by your margin of error, and you're going to go to the right by your margin of error, and that's going to give you the confidence interval. So we will learn how to compute the error bound or the margin of error, but let's just look at the structure first here in this example. So in 2011, the US Department of Transportation reported with 95% confidence that the average length of a motor vehicle trip in the US was 9.72 miles, whatever, with a margin of error of 0.22 miles. So with 95% confidence, the authors of the report are claiming that the true average length of a motor vehicle trip in the United States is between what and what. So what you're doing here in this example is you are starting with your point estimate. So for us, it's given that the point estimate was 9.72. And then the margin of error was 0.22. So this value here is going to be 9.72 plus 22, which gives us 9.94. And then we also have to go to the left as well. So that's going to be 9.72 minus 0.22, which gives us 9.50. So with 95% confidence, the authors of the report are claiming that the true average length of a motor vehicle trip in the United States is between 9.50 miles. So I think they're just asking for the number, but you want to make sure that you include your units when you are evaluating or interpreting a confidence interval. So 9.50 miles and 9.94 miles. The level of confidence for this estimate is, well, it's just the 95% that they gave us. Right? So you're just saying that, the Department of Transportation is not going to go out and collect data from every single motorist in the United States, that took a trip in 2011. It's unfeasible. It's ridiculous. So, right, we talked about samples early on in term. So they take a sample, that sample, they compute X bar, right? In the way that you would normally compute an average of a sample or the mean of a sample. So that becomes your point estimate. And then they say, okay, now we've computed this margin of error, and I'm just going to go left by my margin of error, and I'm going to go right by my margin of error. And that kind of gives me this interval, this confidence interval. And then, we're 95% sure that the actual mean, mu, the parameter of the actual population, is somewhere between 9.50 and 9.94. So you're kind of just like casting a net and saying like, hey, my net's really good. I'm 95% confident that if I cast this out here, it's going to contain the population mean. Oh, and the area under here, this is 95%, right? That goes with how confident you are. So you can think that, if we had a 90% confidence interval, how does that change? If we were only 50% confident, how does that change, what our confidence interval is? And we'll look at things like that. So the next thing we have to talk about is this alpha issue. So when we have a 95% confidence interval like we just saw, what that means is if this is 95% in the interior centered at the mean or the point estimate X bar, then I have 2.5% here in the right tail, and I also have 2.5% in my left tail. So notice, I'm going to kind of recopy this image here. So just for our example, notice that Our interval was from 9.5. We had the mean, our point estimate was 972. And then we had 994. And we just saw that the middle part was 95 and the outside had 2.5 on each side. So what's happening here is there's something called alpha. So alpha is related to the confidence level, CL, as the complement, right? So if your confidence level is 95%, they're always going to be given to you in percentages. So let's convert it to a decimal, right? So this is the area in the blue shaded region. So what alpha is, it's the area in the tail. So it's the area that is outside here, right? So alpha would be 1 minus 0.05. But that's the total area of these pink tails. And so when we're going to compute our critical value for Z, we're computing a Z score, we often just jump straight to alpha over 2. And so if you're wondering where alpha over 2 comes from, it's the fact that you're splitting up this 5% or this 0.05 on each side. And so we're going to see notation that looks like this. So here we have Z of 0.025. And so what that means is just the Z score it's just the Z-score where whatever that little number is, that subscript, that's the percentage, or as a decimal, right? It's given as a decimal of the area that's on the left. So a general form for this, we just did it with 0.95, but just in general, what's going to happen here is you're going to have your normal distribution. You're going to have your point estimate X. And then you're going to have, let's say you wanted a 95%, let's say you wanted a 90% confidence interval. How about that? Switch it up a little bit. It doesn't matter what it is. This is going to be your confidence level. And then you're going to have your Z alpha over 2, right? And so this is going to be alpha over 2 area on this one, and you're going to have alpha over 2 area on this one. And remember that the confidence level and alpha are complements of each other. So if your confidence level is 70, alpha is 30, and you've got 15% in each tail. If your confidence level is 99, alpha is 1, and you've got a 0.5% in each tail. And we will practice this a bunch. And guess what? Excel will compute it for you. Alrighty, so let's actually do an example here. So we're still starting off kind of nice and slow. We're not computing the EBM yet. It's still given, but let's see if we can parse it out. So in this example, suppose we have collected data from a sample. We know the sample mean, but we do not know the mean for the entire population. The sample mean is 7, the error bound for the mean is 2.5, right? So what we're saying here is that we're going to construct our confidence interval just like this. This is always our point estimate here. Then it says that the error bound is 2.5. So that means that I'm going to go up to 2.5, and that's going to give me 9.5. So here we have this distance and this distance, right? This is plus the error bound for the mean, and this is minus the error bound for the mean. I should really have directional errors here, but whatever. I'm sure you get it. What will I get? 4.5. Then our confidence level is, they tell us it's 95%. So constructing the interval itself, just the point estimate plus or minus the error bound is very straightforward. The work comes with actually computing the error bound. So here we were given everything really nicely. Again, if I were to look at the tails, I would say, maybe I would add that alpha here is 5%. We usually don't talk about alpha as a percentage, although we talk about confidence level as a percentage. So you'll usually see alpha as a decimal, and then for alpha over 2, I've never seen alpha over 2 as a decimal, as a percentage. So all right, so let's work on calculating the confidence interval. So it's important here that the standard deviation used must be appropriate for the parameter we are estimating. So in this section, we need to use the standard deviation that applies to our sample means. So remember that when we had constructed our sample distribution, the standard deviation associated to that sample distribution was the given population standard deviation divided by the square root of n, which was the sample size. So they're just restating that here. And what's going to be really common is that we're going to start seeing the notation transition away from sigma sub x, because it's going to be understood in this scenario that sigma is the population standard deviation. I did include it as much as I could before I myself got lazy, and it was just like, yeah, it's the population standard deviation. So you will see it referred to as the standard error of the mean. You might see it written as SEM. I don't really see this that often, but I have recently. So I just wanted you to be aware. Right, so this fraction, when we took the standard deviation for the sample means, right? What we lovingly used to call sigma x bar, how that was equal to sigma x over the square root of n. So this is getting confusing now, right? Or maybe it was from the outset. You're like, can we have less x's, please? So on the left side, x bar, this is talking about This is our sample distribution that follows normal. Here, X was just some possibly unknown random variable. And so then sigma capital X was our population standard deviation. And then sigma X bar was the way of getting the standard deviation for our random variable capital X bar. And you're like, okay, wow, this is a lot. So what we're going to do, and I guess I feel a little bit more justified now when I'm telling you that they're just renaming this something else. I think it actually helps. So we're just going to consider that sigma sub X bar is just the standard error of the mean instead of calling it the sample distribution standard deviation. All right, so we know from before that X bar is normally distributed with mean mu sub X, right? So again, this was our population. Mean. And then sigma X over square root of n, right? That's just the standard deviation of the sample mean, which we are now calling the standard error of the mean. Okay, so when the population standard deviation sigma sum X is known, we use a normal distribution to calculate the error bound, meaning that we're going to find a z-score to compute the error bound of the mean. And not surprisingly, that z-score is z alpha over 2. When we move on to 8.2, the main difference is going to be that we won't know the standard deviation from the population, and we're going to use a t-score to compute the error bound for the mean. And the t-score is just like a z-score, but it's from a student's t distribution, and that's going to be written t sub alpha over 2. All right, so in the land of normal, which is where we are because we know our population standard deviation by some sort of small miracle, we are now going to construct a confidence interval. So again, we don't know the population mean. And the whole point of this exercise is to be like, hey, I don't know what my parameter is for my population, my mean. I don't know what my population mean is. And I'd like to, take a guess at what it would be. And I want my guess to be a really good one. And I want to be very confident in my answer. In fact, I want to be so confident that I'm, 95% confident, or maybe I'm 99.7% confident or whatever. So the first thing that we're going to do is we need to find the value of z that puts an area equal to the confidence level in the middle of the standard normal distribution. What? That sounds very wordy. But really all you're saying is that, okay, we know that we know that X bar as a random variable is normally distributed because the central limit theorem. So all we really want to do is say, hey, what does this value have to be so that I've got, I don't know, just for example, I know we're using 95 a lot, but just for example, right? So what do these values have to be so that I've got my confidence interval? That's what they're saying. We need to find the value of z that puts an area to the confidence, an area equal to the confidence level in the middle of the standard normal distribution 0, 1. So basically what you're saying is that we need to find the z-score associated to X bar. Right, and we have Excel that does that. We say, okay, here's my distribution. It's not standard normal. Like they're saying it has to be standard normal, but Excel does that for us. So we're gonna tell Excel what our population standard deviation is. We're going to give it our point estimate, and then it's going to say, okay, this is a sampling distribution with mean and blank and standard deviation blank. And then we're going to tell it how accurate we want it to be, and it's going to give us our z-scores, and it's going to compute, well, it's going to compute the whole thing. It's really nice. So the confidence level, CL, is the area in the middle of the standard normal. And so the tails are going to split into A over 2, right? And we've seen this a million times. If this is CL, then remember that alpha would equal 1 minus 0.95. So this is just going to be alpha over 2, and this is alpha over 2. Right, so that's where we get Z alpha over 2 by, and we get a Z-score. The next thing we have to do is calculate the error bound. So basically, this is just your critical value or your Z-score times the standard error of the mean. That's it. And then voila, then you just put it all together like we did in the beginning. And then we've got a little template here. If you want to write a sentence to interpret the context, this is pretty straightforward. Like we estimate with blank % confidence that the true population mean, which you want to give some units or context or what you're measuring, is between blank and blank. So that's a lot of information. Let's just try it. Let's just try to do an example here. So from this, we just want to pluck out the relevant information. So we measured 26 textbooks weights. We find that they have a mean weight of 66 ounces. The population standard deviation is 8.3 ounces, and we want to construct a 99% confidence interval. So, all right, let's just get it down. So we've got 26 textbooks. That's going to be N. We've got N equals 26. That's our sample size. Then we find that they have a mean weight of 66 ounces. So I know we've been talking about this as mu sub X bar, but that's not really appropriate. We're just going to call it X bar, lowercase x bar, because we're talking about a particular sample here. In the other case, that mu of X bar, that was the mean for the sampling distribution. This is just a point estimate, a mean of a particular sample. It was 66. And it tells us that the population standard deviation is 8.3 ounces. So you can see here that we've shifted away from the notation sigma subcapital X and moved it just into sigma, right? So this is my laziness. I think Excel will still show sub X, 8.3. And then our confidence level is equal to 0.99. All right, so now let's show how this is all worked through. By hand, what you're gonna do is you're gonna have your point estimate, right? So we always have X bar minus EBM, X bar plus EBM, where we know X bar already and we have to compute the error bound for the mean. And so that's going to be Z alpha over 2 times the standard error, which is sigma over the square root of N. And in this case, Z alpha over 2. So from the confidence level, we know that alpha equals 0.01. And so alpha over 2 would be 0.005. So this is going to give me Z sub 0.005. And then I have to multiply that by sigma, which was 8.3, divided by the square root of our sample size, which was 26. And so if I wanted to look up, if you're wondering, like, what is Z sub 0.005? What you're saying is really you have a normal distribution like capital Z is a normally distributed random variable with mu 0 and standard deviation 1. And so you're just trying to find out what value over here is going to give me 0.005 area to the left. But we have Excel that does all this for us. So let's look at that now. So in our chapter 7 and 8 Excel workbook, there's a tab on the bottom that says 8.1 CI for mean with known st.dev. And so what's going to happen is this is the one we're going to use when we know the population standard deviation. So what we're going to want to do here is we're just going to want to put in our population standard deviation, which is 8.3. So we'll have to put in our point estimate as well, which was 66. And we have to give it the sample size, which was 26. Okay, so what that does for us is it helps us determine what the distribution is for the sample mean. But we still have to do the work of determining what our confidence interval is. And that confidence interval is going to depend on our confidence level. So we have everything we need to construct our confidence interval except for the confidence level. So when we plug that in, we're going to go over to the table that says construct a confidence interval. And remember that every box that is green is something that you want to feed a value into. So if we notice for constructing a confidence interval, it's asking us for the confidence level as a decimal. So this is going to be 0.99. And when you hit enter, what happens is, well, the whole thing gets done. But so it tells you what your alpha is, right? 0.01. And then it computes your z-score from that alpha. So it's telling us that our z-score is, and I want you to think of it as like a plus or minus, right? Because if we kind of go back to this diagram here, we're going to have negative 2.56 standard deviations to get us to the left side, and we'll have positive 2.56 standard deviations to get us to the right. Then, because the standard error was already computed when we put in our population standard deviation and our sample size, the error bound for the mean just takes the z sub alpha over 2 and multiplies it by the 1.63. And so it crunches out 4.1928. And then from there, you'll get your confidence interval. So what we're saying is that the actual mean, we're 95% confident that the actual mean is contained between these two numbers. And again, that's kind of like the colloquial way we talk about it. So what I would do if I was, let's say, turning in work, I would probably just take a snapshot of this. Not that the graph is important. Actually, I could just do this. And there, so now you have your confidence interval. So the next question is asking, what would happen if you measured 49 textbooks and we still have the same mean and standard deviation? So really what we're asking is, how does sample size affect the size of width, length, whatever of the confidence interval? So to answer that question, I'm just going to go ahead and say, okay, well, what if our sample size was 49? Right, so it changes a little bit. I'm just going to go ahead and grab, grab the info. Let's try that one more time. So if we look at this really quickly, let's compare the two. The first thing that jumps out at me is the fact that so what it actually shows you is that, first of all, the error bound is changing, right? Because it depends on the standard error. So in the first case, our standard error, which, by the way, you could kind of just pick up here, shows us that when we had 26 as our sample size, our standard error was larger than when we had 49. So because our error bound for the mean and our margin of error is directly proportional to the standard error of the mean, if I have a large standard error of the mean, I'm going to have a larger margin of error. And that's exactly what we see. We see that our error bound for the mean, or our margin of error, is 4.19 versus, in the case with the larger sample, it was 3.05. So a larger sample gives us more accuracy, meaning that we can be as confident on a smaller interval. A larger sample size means that I can have as much confidence, but with a narrower range of values. All right, so in this next example, we're going to measure watermelons. Okay, whatever. So we've got 25 watermelons weights, and we find that they have a mean weight of 30 ounces. So 25 is my sample size. I'm gonna go ahead and put that in here. I find that they have a mean weight of 30 ounces. So that's gonna be my point estimate X bar. And we know that we're given that the population standard deviation is 5.2 ounces. So that's my sigma. And so from that, right away, I see that my standard error for the mean is 1.04. I want to construct a 95% confidence interval. So I've just put in 0.95. And it constructs the interval for me. It tells me what my alpha is. It gives me my z-score. And then it computes my error bound for the mean, or my margin of error. And then it spits out my confidence interval. So I can go ahead and kind of just take that to show what I did to compute this. And now in this next part, it's saying, hey, let's construct an 80% confidence interval and a 98.7 confidence interval. So for 80%, we want to do 0.80. So I'm just going to steal these little parts right here since everything else is the same. And then we also wanted a 98.7, so 0.987. So now we're asked, how does the level of confidence affect the size of the interval? So our confidence level affects the size of the interval. So looking at all these three, because remember that what really affects the size of the interval is the margin of error, right? How far left and how far right can we go? The margin of error is the product of two numbers. It's your z-score, right? Which is determined directly by your confidence level. So that's how your confidence affects your margin of error. And we also have that the standard error of the mean is part of the margin of error. And so we just saw that in the previous example, right? That when our standard error is small, our margin of error is small, and vice versa. We're seeing the exact same thing with our confidence interval. When we have a large confidence level, then our margin of error is going to go up. So now here's the thought question. If we want a higher level of confidence, and oopsies, and we don't want to increase the width or length of our interval, what would we have to do? Well, if we want to increase our confidence, we're going to have to simultaneously shrink our standard error. And the way that we shrink our standard error is by increasing the sample size. I want to show you one more thing. On the bottom right of your Excel table, I'm not going to fudge with the point estimate or any of this other stuff. I just want to look at something regarding sample size. So my point estimate is 5.2. My standard deviation is 1.04. If I want to be within what is this? Watermelons? If I want to be within 1 ounce of the mean, right? That's my error bound, 1. But I still want to have, let's say, a 90% confidence level. I would have had to get 74 watermelons. If I wanted to have a 99% confidence interval, I would have needed 180 watermelons. So again, I'm not changing my error bound. I'm saying I want my error bound to stay at a fixed width away from, the mean, or I want my interval to have a certain width. And what I'm doing is I'm changing my confidence level. So the more confident I get, let's say I had 0.999, I would need almost 300 watermelons. That's a ridiculous question. All right, well, that does it for confidence intervals when the population standard deviation is known. I will see you next time for when the population standard deviation is unknown.